In equilibrium, it is, as Dalvin said, a state of balance. But it's when the rate of the forward reaction equals the rate of the reverse reaction. And in our example of the two buckets with the water in them, it doesn't mean the amount of water is equal. It also doesn't mean the reaction has stopped happening because you're still transferring water between the two buckets. It's just the rate of transfer is equal. Equilibriums are dynamic equilibriums. Dynamic means that it's still moving forward and it's still moving backwards. It's just moving forwards and backwards at the same rate. For equilibrium reactions, they're usually written to look like this. NO2 gas yields N2O4 gas. That is an equilibrium reaction. And it's still balanced. What's the difference in how you write an equilibrium reaction? It's the arrow. And y'all have probably seen reactions with those arrows before, but those arrows mean that this is an equilibrium reaction. Not all reactions are equilibrium. Okay, sometimes they just react and they make product and they stop because they're finished making product. But some reactions are equilibrium. They're going back and forth. It's just the rate that N2O4 is being produced equals the rate that N2O4 is reacting to make the NO2. The rate of both reactions are equal. For equilibrium reactions, we have equilibrium constants. An equilibrium constant is given the symbol KEQ. The little EQ is like a subscript to denote that it's an equilibrium constant. And it's a capital K. We just finished doing kinetics, and the rate constant in kinetics was the lowercase, the little cursive K. Okay, but this one's a capital K. So how do you write an equilibrium constant? Remember this little template that I used to introduce rate laws and kinetics? What do the lowercase letters mean? Coefficients. Uppercase letters are the components of the reaction. Y'all, an equilibrium constant is products over reactants raised to the power of the coefficient. In other words, for this reaction, the equilibrium constant, it would be the concentration of the product, C, raised to its coefficient, times the concentration of D, raised to its coefficient, its products, divided by the concentration of the reactants, A, raised to the power of its coefficient, a little a, times the concentration of B, raised to the power of little b, its coefficient. Go back to this reaction I just wrote at the bottom. How would you write an equilibrium constant expression for that reaction? Not putting numbers in, just putting in the components. The equilibrium constant will be equal to what? Yeah, very simply, the concentration of N2O4 raised to the first power, which you don't have to write because it's understood to be 1, divided by the concentration of NO2 squared because the coefficient is 2. There's some catches when you're writing equilibrium constant expressions. In this reaction, the NO2 is a gas and the N2O4 is a gas. But y'all know, besides gas, what kind of other things can you have? You can have gases, you can have liquids, you can have aqueous, you can have solids. The only stuff that shows up in an equilibrium constant expression it has to be either a gas or aqueous. Never include solids or liquids in the equilibrium constant expression. The only stuff that shows up has to be gas or it has to be aqueous. Page 638 has some practice problems there. The first practice problem says that SiCl4 gas plus 2 hydrogen gas is in equilibrium to make Si solid and 4 moles of HCl gas. What would the equilibrium constant expression for that equation look like?
What do you do with the solid?
You just don't include it. You just leave it out. It's going to be products, which just the HCl raised to the 4th power, divided by reactants, the SiCl4, and the hydrogen squared. Now let's work a problem.